Alright, welcome back to our final example of how to solve now more complex circuits. So these are sometimes referred to as combination circuits because they have elements that are both series and parallel. So here's our given example of our friend right here. As you can see, this is in series, but this is in parallel with this group. So we have two things going on at once here. So we can't purely use our rules for series, and we can't purely use our rules for parallel. So we have to figure out, how do I make this ugly circuit into something I can manage? So the way to do that is to first simplify the resistors. So here I see two resistors that are in series with each other. And so if I remember correctly, the rules for series is that resistors add up. So if I want, I could fundamentally replace this with a single 6 ohm resistor. And if I do that, I'm going to get the exact same current flowing through this branch as I would if there was the 4 and the 2. So I really haven't changed much. Also, the total voltage drop is also the same. So again, haven't changed anything. I'm just simplifying it so we can now use our rules. So what this really does is, if I want, I can redraw the whole thing, which I'll just do. Now I have this. I've got a 6 ohm resistor and a 3 ohm resistor. And they are now creating a circuit that looks like this. So we can now treat this is 12 volts, treat this just as if it was, hey, it looks like a parallel circuit. So now we can go through all of our steps. So if we go through all of those steps, grabbing some colors here, then I can say, well, that's my V, what's my I, and what's my R. So V equals I equals R equals, V equals I equals R equals, and I can just kind of play my game of Sudoku. So if I do this, the voltage here is 12, the resistance here is 6 ohms, the resistance here is 3 ohms. And so if I do this, I could say, well, the total resistance, since it's in parallel, if I did that, I got 1 over the equivalent equals 1 over 6 plus 1 over 3. So I basically have 1 over 6 plus 2 over 6. So I really have 3 over 6, which equals 1 over REQ. Don't make the mistake. Remember to flip it. So really, my equivalent resistance equals 2. Probably shouldn't be an equal sign. There we go. So then my equivalent resistance of the whole circuit is 2. So I can put a 2 ohms there. And remember, the equivalent resistance is always less than either of the individual resistances when you have things in parallel. So it makes sense. So now I've got a voltage of 12. I've got a resistance of 2, so I can solve for the current because V equals IR. So I has to be 6 amps. Well, cool. Plus, these are in parallel, so I also now know that the voltage here is 12, so then I know the voltage here is 12, so 12 volts, and the voltage here is 12 volts. So if I want, I can use Ohm's law again, and I can say, I must be 2 amps. I must be, for this guy, I must be, where's my brain? 4 amps, there we go, yay brain. Sometimes it's a little slow, don't judge me. And I can check, say, hey, look, 6 amps, 2 amps, 4 amps, that's all good. But the problem is that was for this, that wasn't for this. Oh man, did I waste my time? I don't know, did I? Let's find out. Well, this is still true for this guy. Okay, all of this is still true. So I'll just kind of mark this. So this stuff is all good. That is not the color I wanted at all, and it knows it. Oh no, now the computer's being all jerky on me. Alright, so that's not the color I wanted. I want this pretty color here. Alright, so this stuff is all good. Okay? And the 3, well, that stuff's all good for the 3 too. So that stuff's still okay. The question is, what from this can I use here? Well, these are in series. So one thing I know about series is the current is the same. So I really know that the current is going to be 2 amps. So 2 amps here, 2 amps here. So now I can use Ohm's law to solve for the voltage. So V equals IR. So therefore my voltage is equal to, here, 8 volts, and my voltage here is equal, for the 2, is equal to 4 volts. And since they're in series, the total voltage in series adds up. So 8 plus 4 is 12. Okay, so I can still use all that information. So when you simplify something, you can basically break it down as far as you want, and then you can go back and you can re-expand it, and you just have to kind of figure out, okay, how do I use this information? So there's a multitude of ways to solve these problems. It all depends on what you're given, but I always joke it's like playing Sudoku, because you just say, oh, V, I, and R for everything, and then you solve. Not too complicated, as long as you just go through it nice and slow. Now, that's not the end of the road. There is one more thing that I want to talk about before I let you go do homework or whatever you were doing before you decide to watch this. I'm sure you're doing homework. That's all you do, right? No fun. And let's talk about, where are you going? Let's talk about power. All right, power. All right, now you know power. Power is equal to the rate at which energy is used. All right, so it's energy, or I should say change in energy, over time. So that's your definition of power. So we often want to know, hey, which resistor requires the most power, or which light bulb is going to have the greatest wattage, because we know watts is power. So we want to figure this stuff out. Or if you have an awesome sound system, how cool is it? It's got more power. Oh, yeah, okay. So to figure out the equation for power, well, that's energy per unit time. Well, if you remember, volts is energy per unit charge. All right, so this is volts. And current is the rate at which charge passes through the circuit. So that is the amount of charge that passes through in a given amount of time. Well, if you multiply these two, as I've preemptively done, charge cancels out and you're left with energy per unit time. So that means the equation for power when it comes to electricity is voltage times current. So you'll often just see this simplified and written as power equals current times voltage. So you'll probably also be asked to solve for, which is the most powerful resistor or anything like that. So it uses all the information we've already deduced from solving our circuit problems, and now we just say, hey, I need to know the power. Which, what was the power usage on this guy? So I'd simply take its current, 4 times its voltage of this, so I could say, hey, your power was 48 watts. And hey, what was your power over here? The 6 total. Or I could break it down. I could say, hey, your power is 8 watts, because it's IV. And your power equals 16 watts. So I could figure out, hey, which is the one that requires the most power? And clearly it is the 3. All right. So you can break it down like so. All right. That's about it. That's all the stuff I got for circuits. So really, this is one of those things you just got to practice until it kind of makes sense. And I honestly treat it more like a game than logic, but it's all based on knowing those rules of series and series and parallel circuits. So if you don't know those rules, then you're going to be in trouble dealing with the complicated ones. All right. See you on the flip side.